Imagine standing in the Atacama Desert, beneath one of the cleanest, darkest skies on our planet. The stars are so abundant that they look like sparkling dust scattered across dark velvet. Suddenly, a robotic telescope detects a light source with no obvious explanation. It's not a typical asteroid, not a comet whose origin we know, but something coming from very far away, moving at such extreme speed that it contradicts everything we understand about motion in interstellar space. That burst of light received a scientific designation, 3I/Atlas. But within those letters and numbers lies one of the most baffling stories in contemporary astronomy. Because this object isn't just fast, it isn't just ancient, it doesn't just come from enormous distances. According to our mathematical calculations and the laws of physics as we know them, this object should never have reached us. And yet, here it is, moving at 58 kilometers per second relative to the Sun, a staggering speed that makes the two previous interstellar visitors look almost motionless. Oumuamua traveled at 26 kilometers per second, Borisov at 32. This new visitor surpasses them easily, leaving them behind as if they were standing still. The disturbing part is this: that velocity is not the result of solar gravity, not a side effect of gravitational slingshotting. It is its inherent speed, the excess it carried before even entering the solar system. Something somewhere in the dense galactic region accelerated it to that point, and we have no idea what it was. It could have been a dying star, a compact molecular cloud, a close pass by a massive planet, or something we haven't even conceptualized yet. The only certainty is that 3I/Atlas traveled through empty space for billions of years, crossing regions where the stars are older and contain fewer heavy elements than our Sun. And by mere statistical coincidence, it passed close enough to be detected, photographed, and chemically analyzed. But for several weeks before its official identification, it was completely invisible, not because it was tiny, but because it was moving directly in front of the bright core of the Milky Way, lost among millions of background stars, eclipsed by the luminosity of the galactic center. When it was finally identified on July 1st, it was already heading toward its closest approach to the Sun, scheduled for October 29th at 11:44 Universal Time Coordinated. During that critical period, it will be positioned between the Sun and us, totally unobservable from Earth. Only specialized coronagraph instruments, like LOSCO aboard the Soho Observatory, might capture its transit if conditions align perfectly. Even that is uncertain, because its apparent magnitude is around 11.5, far too dim for casual observation, and its minimum separation from the Sun will be only 2.59 degrees on October 21st. What we have is a restricted, fragmented observation window, constrained by orbital geometry. But instead of discouraging us, this should fascinate us, because it means every measurement, every spectral analysis, every Hubble or James Webb photograph is a temporary gift, a brief glimpse of something we will not see again for millennia. So the truly important question is not just what 3I/Atlas is, but what it is telling us about the universe that we are failing to fully perceive. What information does it carry in its composition, in its trajectory, in its improbable age? And more importantly, do we even have the mental capacity to recognize that there are cosmic entities traveling between stars that violate our usual classifications, our assumptions, our very idea of what is possible? Because if 3I/Atlas exists, if it is here, if we can observe it, then our understanding of how comets originate, how objects are ejected, how galactic mechanics operate, all of it needs to be reconsidered. And that is where the true beauty of scientific exploration lies. Not in the answers, but in the questions that force us to rethink everything from the ground up. If this kind of reflection resonates with you, if you enjoy diving deep into cosmic analysis with room for contemplation, I invite you to join this exploratory community on the channel. It's an invitation to think differently about our universe. And if you have your own questions, doubts, or ideas about 3I/Atlas, leave them in the comments section. Scientific progress advances when we exchange wonder and share our perspectives with others. The official discovery of 3i/Atlas took place on July 1st, 2025, thanks to the robotic Atlas telescope, supported by NASA and operated from the Rio Hurtado Observatory in Chile, under Observatory Code Bloveto 68. At the moment of its detection, it showed an apparent magnitude of 18, making it completely undetectable to the naked eye and even difficult to spot with conventional telescopic equipment. It was approaching the inner solar system at 61 kilometers per second relative to the Sun, located 3.52 astronomical units from Earth and 4.53 from the Sun. It was crossing the border between the constellations Serpens and Sagittarius, right near the galactic plane, which obstructed its initial recognition because that region has an extremely dense star field. It received the provisional classification A11/PL3Z, and the information was sent to the Minor Planet Center of the International Astronomical Union. What initially looked like a particular trajectory that could intersect Earth's orbit soon revealed its true nature, a hyperbolic path not gravitationally bound to the Sun, showing a hyperbolic excess velocity of 58 kilometers per second. To visualize this, the escape velocity from the solar system at Mars distance is about 24 kilometers per second. 3i/Atlas travels at more than twice that speed. At such velocity, no gravitational interaction with the inner planets could have accelerated it. This confirms unequivocally that it comes from beyond the solar system. Subsequent observations by professional institutions and independent astronomers corroborated its interstellar origin. Archival data was found. The transit facility captured the visitor between June 14th and 21st. Atlas itself had recorded it without recognizing it between June 5th and 29th. A dedicated astronomer noted that it went unnoticed at first because it was crossing the crowded fields of the galactic center, where any faint object disappears into visual noise. On July 2nd, multiple observatories in Chile, Arizona, and Hawaii confirmed that it was not an inert asteroid but a dynamic comet with an enveloping atmosphere and a possible tail-like extension of 3 arcseconds. The Minor Planet Center formally announced the discovery, assigning it the designation 3I, indicating it is the third confirmed interstellar object after Oumuamua in October 2017 and Borisov in August 2019. It also received the classification of non-periodic comet C/2025 N1 Atlas. By the time of its official naming, 122 observations from 31 different observatories had already been collected. The Transiting Exoplanet Survey satellite had observed it prior to identification between May 7th and June 3rd. Those measurements indicated that it was already brightening and showing activity even at about 6.4 astronomical units from the Sun. This is crucial because at that distance, water ice does not evaporate efficiently, which means its activity cannot be driven primarily by the sublimation of water. Unlike most comets we know, something more volatile must be generating its atmosphere, something that evaporates at much lower temperatures. On July 20th, near-infrared observations by specialized observatories detected the presence of frozen water in its atmosphere. But the real surprise arrived on August 6th, when the James Webb Telescope focused its spectrographic instruments on the comet and revealed its composition with unprecedented precision. The findings were spectacular, an atmosphere dominated by carbon dioxide, with a CO2 to water ratio of 8:1. For reference, in most comets in the solar system, that ratio is close to 1:1 or even lower. Only one other documented comet breaks this trend so dramatically. 3i/Atlas also showed smaller amount of carbon monoxide, carbonyl sulfide, and, surprisingly, atomic nickel vapor, confirmed by specialized observatories on July 20th. The detection of nickel was so unusual that it initially generated skepticism, but multiple reviews between July and August confirmed not only its presence, but an ongoing increase in its concentration as the comet approached the Sun. This suggests that the nickel is not being released by direct evaporation of frozen metal, which is physically impossible, but probably by chemical breakdown of organic compounds that incorporate nickel through cosmic weathering processes, such as nickel tetracarbonyl. But here lies the dilemma. We don't know how those compounds ended up in the comet in the first place. That leads us to deeper questions about where and how 3I/Atlas originated. The chemical composition of this visitor, its atypical abundance of carbon dioxide, its provenance from the thick galactic disk, all of it points to an intriguing possibility. This object may have formed much farther from its parent star than any comet in our region, beyond the boundary where CO2 freezes, in a territory where temperatures were so low that carbon dioxide solidified directly. Some researchers propose, making it clear that we're still in unconfirmed hypothesis territory, that 3I/Atlas could be a remnant of an extraordinarily cold protoplanetary disk surrounding a star poor in heavy elements, with a metallicity at least 40% lower than that of our Sun. If that were true, we would be witnessing a type of object never before analyzed, a comet formed under chemical conditions radically different from those of our solar environment. But there is also another possibility, that it has an unusually thick and insulating surface layer that limits water evaporation, hiding reservoirs beneath the surface, and skewing our readings toward more superficial volatiles like CO2, or that it has experienced cosmic radiation bombardment for billions of years, transforming its surface composition in ways we don't yet fully understand. Science does not have all the answers yet, and that, instead of being a limitation, is its strength, because it means we are building understanding in real time, revising our theoretical frameworks, refining our perspectives. The trajectory of 3I/Atlas is hyperbolic, with an orbital eccentricity of 6.14, the most extreme of any identified interstellar object. For context, Oumuamua had an eccentricity of 1.2 and Borisov 3.4. This comet nearly doubles the previous record. Such a severe eccentricity makes its path almost a straight line rather than a smooth curve around the Sun. Its orbit is inclined 175 degrees to the ecliptic, which means it moves retrograde, opposite to the planets, but coincidentally well aligned with respect to the solar system's orbital plane, deviating by only 5 degrees. That alignment is pure statistical luck, but a luck that favors us because it made detection relatively easy. The closest approach to the Sun will occur on October 29th at 11:44 Universal Time Coordinated, with an uncertainty of just 2 minutes. At that distance, 1.36 astronomical units, it will sit between Earth's and Mars' orbits, moving at its maximum speed of 68 kilometers per second relative to the Sun. That is faster than the escape velocity at the Sun's surface, but extraordinarily fast for an object at that distance. After perihelion, it will pass by Venus on November 3rd at 0.65 astronomical units. Then it will approach Earth on December 19th at 1.80 astronomical units. Too distant for naked eye visibility, but observable with medium-sized telescopes. Finally, it will approach Jupiter on March 16th, 2026 at 0.36 astronomical units. Some have suggested that the Juno spacecraft, currently in Jovian orbit, could be reoriented to study it during that encounter. However, this is unlikely. Juno has limited fuel and is facing mechanical issues, though the theoretical possibility exists, and that alone is exciting. Every time an interstellar body passes near a planet with active missions, we gain a singular opportunity to study it from multiple perspectives, using instruments normally dedicated to other objectives. 3I/Atlas has an apparent magnitude that fluctuates between 11.5 and 6, depending on its distance to the Sun and its level of activity. For context, magnitude 6 represents the detection limit for the naked eye under rural skies without light pollution. Magnitude 11.5 requires telescopes with apertures between 7.6 and 11.4 centimeters and skies free of artificial lighting. Still, observing it is challenging because its diffuse coma scatters light in a way that reduces its apparent brightness. A point source is easy to detect. A diffuse atmosphere looks much dimmer, even if it has the same nominal brightness. During its closest approach, it will be behind the sun from our viewpoint, totally invisible even to the most advanced instruments. The only possibility during that interval is space-based coronagraph telescopes, devices designed to block solar radiation and reveal bodies near the sun. The LOSCO instrument aboard the Soho Observatory, for example, can detect comets down to magnitude 7 or 8 if they fall within its field of view. However, there's a complication. Those instruments have a restricted angular reach and are calibrated for comets that pass very close to the sun, generally within 0.1 astronomical units. 3I/Atlas will pass much farther away. Its minimum angular separation will be 2.59 degrees on October 21st, which places it right at the edge of the instrument's field of view. The probability of coronagraph detection is low, though not impossible. If the comet experiences a sudden outburst, an episode where it ejects enormous volumes of dust and becomes temporarily much brighter, it could appear even under adverse conditions. That has happened before with local comets. Some have increased significantly in brightness days before perihelion due to fragmentation and intense gas release. But it is equally possible that 3I/Atlas could disintegrate completely, as happened with Borisov, which fragmented into multiple components after its closest approach. If that occurs, we could lose it permanently or witness a live disintegration spectacle. Nobody knows. And that uncertainty, that feeling of witnessing something that could transform instantaneously, is part of why astronomy is so viscerally captivating. Some astronomers published an analysis suggesting that 3I/Atlas could be an extraterrestrial spacecraft with hostile intentions. Their reasoning rested on 3 alleged peculiarities: an apparently disproportionate size for such a faint comet, the initial absence of identifiable chemicals in early spectra, and a trajectory that, according to their argument, was suspiciously well-oriented with respect to the ecliptic, as if intentionally guided. That paper triggered an immediate storm of criticism from the astronomical community. The prevailing view is that 3I/Atlas is, without question, a natural comet. Subsequent observations by the James Webb Space Telescope confirmed the presence of carbon dioxide, water, and carbon monoxide, all classic markers of cometary activity. Leading astrophysicists pointed out flaws in statistical analysis regarding trajectory, arguing that its positioning falls within expected ranges for interstellar objects identified from Earth, simply because our telescopes are optimized to track bodies near the ecliptic. Others emphasize that while it is valuable to keep an open mind toward any testable prediction, the presented evidence is not extraordinary, and extraordinary claims require extraordinary evidence. Why do I bring this up? Not to endorse a hypothesis lacking observational robustness, but it illustrates something deeper about how contemporary science works. Speculative conjectures, even controversial ones, have a place in the investigative process, provided they are clearly labeled as conjecture and remain open to refutation by data. The conflict arises when those conjectures are presented as definitive truths without adequate evidence, or when they are exploited to generate sensational headlines. In this case, it was dismissed quickly by the community, not to shut the door on unusual possibilities, but precisely because the accessible information overwhelmingly suggests a natural explanation. And that in itself is a reminder that science works. It can be slow, it can be conservative, but it is self-correcting. Bad ideas are weeded out. Good ideas are refined, and extraordinary assertions demand extraordinary proof. The Hubble captured high-definition images on July 21st, revealing peculiarities in its atmosphere and narrowing the size of its nucleus to between 0.32 and 5.6 kilometers. There's great uncertainty in that measurement because the nucleus is coated in a reflective dust atmosphere, making it appear brighter and larger than it truly is. Earlier analyses from July suggested potential diameters of up to 10 or even 20 kilometers, but later revisions showed those projections were excessive. The calculated dust loss rate suggests the nucleus is likely under 1 kilometer in diameter, comparable to Borisov. That makes it a tiny, fragile, short-lived object, and yet it has endured for billions of years in the void, facing cosmic radiation, energetic particle bombardment, gravitational encounters with stars, and dense clouds. It is an extraordinary survivor. The atmosphere photographed on July 2nd stretches roughly 26,400 by 24,700 kilometers, nearly twice Earth's diameter. That is disproportionate for such a small nucleus. And there is more. Research in August revealed an even larger gaseous carbon dioxide atmosphere, extending at least 348,000 kilometers, detectable only in near-infrared. That gigantic CO2 coma is one of the largest cometary structures ever observed, fueled by persistent sublimation of CO2 ice from the nucleus as it approaches the Sun. Within that atmosphere, small dust particles are expelled from the nucleus at 22 meters per second, while larger particles are released more slowly at roughly 2 meters per second. In July, it was estimated to be ejecting 6 kilograms of small particles per second and 60 kilograms of larger particles per second. Those rates are comparable to Borisov during its approach, but lower than typical distant comets, suggesting that 3I/Atlas is relatively low activity by comparison. Or at least it was in July. As it approaches perihelion, those figures are expected to rise significantly. A study published in July estimated, with 68% confidence, that 3I/Atlas is between 7.6 and 14 billion years old, based on the average ages of stars in a thick galactic disk. Think about that for a moment. Between 7.6 and 14 billion years. Our solar system is 4.6 billion years old. The universe is 13.8 billion years old. That implies 3I/Atlas may have formed in the early stages of the cosmos, when planetary systems were younger. Stars contain lower proportions of heavy elements than we assumed, and the chemical conditions in protoplanetary disks were radically different. A parallel analysis estimated an age between 3 and 11 billion years, broadly consistent with the previous result. Both studies are based on decomposing the comet's velocity into galactic components, radial, tangential, and vertical speed. When 3I/Atlas entered the solar system, it was moving opposite the galactic core and also traveling upward through the galactic plane. That vertical velocity is unusually high compared to nearby stars and other interstellar visitors, indicating it follows an inclined orbit around the Milky Way and belongs to the thick galactic disk, a population of ancient stars with lower heavy element content than our Sun. Those stars formed billions of years ago, when the galaxy was younger and less chemically enriched by supernovae. If 3I/Atlas originated orbiting one of those ancient stars, it is literally a cosmic relic, a fragment of galactic history older than our own planet. And that raises profound questions about its composition. How can a body so old still contain volatile ices, such as carbon dioxide, carbon monoxide, and water? Shouldn't they have evaporated eons ago under relentless cosmic radiation? The answer likely lies in the extraordinarily low density of interstellar space. In the void between stars, radiation is strong, but evenly distributed, and there is no atmosphere to trap heat. A comet drifting through interstellar space cools to temperatures near 3 Kelvin, the temperature of the cosmic microwave background. At those temperatures, sublimation of ices is virtually non-existent. The ices remain frozen for millennia, preserved in cryogenic suspension. Only when a comet enters a star system, when stellar radiation begins to warm its surface. Do the ices evaporate and the comet becomes active? That is why 3I/Atlas remained inert throughout its interstellar journey, and only began to show activity when it reached roughly 6.4 astronomical units from the Sun, the distance at which carbon dioxide sublimates efficiently. But here's the real enigma. We cannot trace 3I/Atlas back to its original parent star. It has been wandering the Milky Way for billions of years, more than enough time to be deflected by multiple gravitational encounters with molecular clouds and stellar systems, altering its trajectory in ways impossible to reconstruct without exhaustive modeling. That means we will never know exactly where it was born, but we can infer characteristics of its parent star from its chemical composition and its membership in the thick galactic disk. Its parent star was likely a low metallicity star, with a significantly lower heavy element content than our Sun, probably AK or M-type main sequence star, smaller and cooler than our star, with a closer habitable zone and a more compact protoplanetary disk. At some point after its formation, the comet was ejected from its original system, either by a close encounter with a massive planet or another star. Since then, it has been wandering the galaxy as an orphan object until sheer statistical coincidence brought it near us. Some people, upon learning about 3I/Atlas, feel something beyond intellectual curiosity, a sense of resonance, synchronicity, as if the comet is appearing in their lives at the exact moment they needed a reminder that vaster energies operate in the cosmos, forces that do not govern, but simply witness. Throughout millennia of contemplative and spiritual practices, comets have been interpreted as harbingers of transformation, messengers of the unknown, symbols of change. I am not claiming that 3I/Atlas has purpose or consciousness. That would be projecting human qualities onto a physical phenomenon that simply obeys natural laws. But I am suggesting that symbols exert influence, and that humans have found meaning in comets since we first learned to look at the sky. In archetypal interpretations, an interstellar visitor could represent influences from beyond our familiar environment, energies emerging from outside the traditional patterns of the zodiac. Some would see 3I/Atlas as a bearer of distant information, a reminder that the cosmos is far older and more colossal than our individual existences can ever contain. Others would perceive it as a symbol of transience, a body that appears briefly and then disappears forever, never to be witnessed again. And others would simply regard it as a fascinating physical phenomenon without any added symbolic weight. All of those perspectives are valid. Science tells us what 3I/Atlas is: an ancient cometary visitor with atypical chemistry and an extreme trajectory. Personal interpretation tells us what it means to us as human beings, and both can coexist without conflict as long as we remain clear about which is which. If you feel that 3I/Atlas holds personal significance, if its arrival into your awareness coincides with a moment of transition or introspection in your life, then that meaning may indeed be authentic for your experience. But it is not scientific, it is subjective, and that is perfectly fine. Science does not monitor purpose. It only measures the physical characterization of reality. Now let us return to pure physics, because there is an aspect of 3I/Atlas we have not yet explored in depth: its interaction with the solar wind and the electromagnetic field of the solar system. Comets are not passive entities that merely reflect sunlight. They are dynamic bodies that actively interact with their environment. As they approach the sun, their neutral gaseous atmosphere is ionized by solar ultraviolet radiation, generating a cloud of electrically charged particles. These particles are carried away by the solar wind, a constant flow of charged particles streaming from the sun at speeds between 300 and 800 kilometers per second. The result is an ion tail, an elongated structure that always points directly away from the sun, regardless of the comet's direction of travel. 3I/Atlas shows signs of possessing a very faint ion tail, visible in Hubble images as a weak, wide extension toward the east, away from the sun. But the tail is difficult to observe because it is pointing almost directly toward us, making it appear shortened and largely hidden behind the comet's atmosphere. In addition to the ion tail, 3I/Atlas has a peculiar structure, a dust plume that points toward the sun instead of away from it. That may seem contradictory, but it has a fairly simple physical explanation. The plume is not a tail in the conventional sense, but a burst of dust emitted from the sunlit, heated side of a nucleus, where ice vaporization is most intense. The dust is expelled in the direction of the sunlight because it is being released from the surface facing the star, and it takes time for solar radiation pressure to push the dust backward and form a traditional tail. This behavior is common among distant comets, which also display dust plumes oriented toward the sun when they are far from perihelion. As 3I/Atlas approaches its closest point to the sun, that plume will evolve into a more traditional, curved, extended dust tail. But another electromagnetic phenomenon is also at play: the polarization of light scattered by dust grains in the atmosphere. When sunlight strikes microscopic dust particles, it is scattered in all directions, but not uniformly. The scattered light is partially polarized, with a plane of polarization depending on the size, shape, and composition of the particles. Polarimetric observations of 3I/Atlas could reveal detailed information about the structure of dust grains in its atmosphere, including whether they are compact or porous, rich in silicates or organic materials, and whether they have been processed by cosmic radiation. So far, those observations have not been published, but they are underway, and when released, they will add yet another layer of understanding to this extraordinary object. Think about what it means that light itself can tell us stories about objects we will never touch, never visit, objects millions of kilometers away. Light is information, and we are the receivers of that information. The ability to extract knowledge from photons that have traveled for years is one of the most powerful tools we possess. Now we enter one of the most practical and frustrating questions about 3I/Atlas. Could we send a spacecraft to study it up close? The short answer is no, not with current technology. Launching a probe from Earth after the comet's discovery on July 1st will require a change in velocity of at least 24 kilometers per second, which exceeds the capability of any propulsion system available today. For context, the highest escape velocity achieved by a human-made spacecraft is around 16.6 kilometers per second by the New Horizons probe. 24 kilometers per second is beyond our present reach. But there is one fascinating theoretical possibility: launching a probe from Mars instead of Earth. A study published in July concluded that hypothetical probes launched from Mars between July and September would require a change in velocity of only about 5 kilometers per second to fly by 3I/Atlas in early October. That is far more feasible, though it would still require infrastructure that does not currently exist on Mars: a launch platform, propulsion systems, in situ manufacturing capabilities. But in a future where Mars hosts a permanent human base, where we have the ability to build and launch spacecraft from its surface, then the exploration of interstellar objects could become a reality. For now, our only option is to observe 3I/Atlas from afar with ground and space telescopes. Gathering every photon of information we can before it disappears forever. Some spacecraft already in planetary orbit may have observation opportunities. The Juno probe, in orbit around Jupiter, will pass relatively close when the comet approaches Jupiter on March 16th, 2026. As mentioned earlier, Juno has little fuel left and engine issues, so redirecting it is unlikely. Other spacecraft en route to their destinations will pass at various distances, and commanding them to observe 3I/Atlas will be technically difficult and could jeopardize their main missions. Whether that happens will depend on risk assessments that are still underway, but the possibility exists, and that alone is exciting. If this kind of exploration fascinates you, if you like the idea that we are constantly making decisions about what to explore, what to risk, what to prioritize in space, then I invite you to join the channel. Subscribe for more content that makes you think, that inspires you to question, and that invites you to be part of this cosmic conversation. Leave your comments with your perspectives and questions about everything we've explored today. Finally, let's talk about what 3i/Atlas teaches us about the universe in a broader sense. Every interstellar object we detect is a window into stellar systems we will never visit. It is a silent messenger from places and times far beyond our reach. Before Oumuamua, we had no direct evidence that star systems regularly exchange objects. We had theories, simulations, mathematical models predicting that it should happen, but no observational proof. Oumuamua changed that. Borisov confirmed it, and 3i/Atlas is reinforcing it. We now know for certain that the galaxy is full of wandering objects, fragments of planetary systems gravitationally ejected and traveling through interstellar space for eons. Some are rocky, like Oumuamua likely was. Some are cometary, like Borisov and 3i/Atlas. And there are probably other types we haven't detected yet. Rogue planets, expelled moons, debris from planetary collisions. The universe is far more dynamic, far more interconnected than we once believed. Star systems are not isolated islands. They are nodes in a galactic network of matter exchange, chemical mixing, and element distribution. And that has profound implications for the question of life in the universe. Because if star systems are constantly exchanging objects, then they may also be exchanging potential ingredients for life. Complex organic molecules, amino acids, even microorganisms could be traveling between stars inside comets and asteroids, shielded from vacuum and radiation by layers of rock and ice. The panspermia hypothesis, the idea that life may have originated in one region of the universe and then been distributed elsewhere via interstellar objects, is no longer science fiction. It is a legitimate scientific possibility that deserves serious study. 3i/Atlas does not carry life as far as we know. We have detected no biological signatures in its spectrum. But it is a reminder that the cosmos is constantly moving matter from one place to another, and that the borders between star systems are far more permeable than we once assumed. We are part of a living, dynamic, interconnected galaxy, and every interstellar object we detect brings us one step closer to understanding our place in that network. The atoms in your body were forged inside stars that died billions of years ago. And perhaps, just perhaps, some of those atoms travel between stars inside objects like 3i/Atlas before ending up in the protoplanetary disk that formed Earth. That is not metaphor, it is physics. It is the tangible reality of our place in the cosmos. Take a moment to consider what that means for your understanding of universal interconnection. And this leads us to one of the most valuable aspects of all this, the value of not knowing. We live in a culture that worships answers, certainty, definitive solutions. But science in its purest form is the art of asking better and better questions. 3i/Atlas does not give us answers. It gives us questions. Why does it contain such an abundance of carbon dioxide? How did it survive billions of years without disintegrating? What chemical processes created the nickel compounds in its atmosphere? How many other objects like it are currently traveling through the Milky Way, unseen by us because they are too distant or too faint? And what will we learn when we detect the next one, and the next, and the next? Every interstellar object is unique. Oumuamua was rocky, elongated, and had no detectable atmosphere. Borisov was a classic comet with a composition similar to those in our solar system. 3i/Atlas is something in between. A comet, yes, but with unusual chemistry and an origin in the thick galactic disk. The next one could be completely different. And that is exciting, because it means each discovery expands our catalog of possibilities, our understanding of how nature builds objects in different environments. We are not looking for a single answer. We are building an atlas of cosmic diversity, and 3i/Atlas, despite its technical name and brief appearance, is an important page in that atlas. It reminds us that the universe is stranger, more diverse, more surprising than any single theory can predict. And to me, that is profoundly hopeful, because it means there will always be more to discover, always new questions, always reason to look up and wonder what else is out there. What do we do with all this information? What do we do with the knowledge that a 7-billion-year-old object just crossed our solar system, carrying chemical stories from a time before our world existed? I think the answer is simple. We let it change us, not dramatically, not in a way that disrupts our daily lives, but subtly in how we think about time, about scale, about our connection to the cosmos. 3i/Atlas is an invitation to think in terms of billions of years, not just decades. An invitation to recognize that we are temporary observers of processes that began long before we existed and will continue long after we are gone. And there is something deeply humbling and deeply freeing about that realization. Because if we are that small, that temporary, then our mistakes are too, our worries are too, our anxieties are too. I'm not saying nothing matters. I'm saying everything matters on its appropriate scale. Your life matters on the scale of your life. Human civilization matters on the scale of human civilization. But there are larger, slower scales in which individual concerns dissolve into bigger patterns. And sometimes, just sometimes, it helps to remember that. We have covered the physics of 3i/Atlas, its discovery, its composition, its trajectory, its age, its scientific meaning. We have also briefly touched on its possible symbolic significance, always making clear that this is personal interpretation, not science. And we have tried to maintain a balance between rigor and contemplation, between data and wonder, because both matter. Data tells us what is real. Wonder tells us why we care. If this content has given you anything, I hope it is that a combination of solid knowledge and space to feel. Because science is not just the accumulation of facts. It is a way of relating to the world, a way of being present before mystery without needing to solve it immediately. 3i/Atlas does not give us definitive answers. It gives us questions, data, enigmas, and invites us to sit with them, explore them with curiosity, and let them change us in subtle ways. And maybe, just maybe, when we look up next time and think about that tiny point of light traveling 58 kilometers per second into interstellar space, we will remember that we are part of something much larger, that we are temporary observers of a cosmos that preceded us and will outlast us, and that this, far from frightening, is profoundly beautiful. Thank you for joining me in this exploration of the cosmos and of everything that challenges us to think. If you enjoyed this content, if it helped you relax, learn something new, or reflect on our place in the universe, consider sharing it with someone who might appreciate it. Subscribe to the channel for more scientific and contemplative exploration that speaks to both mind and heart. Leave your thoughts, your questions, and your own reflections in the comments. Science advances when we share curiosity and challenge each other to think more deeply about the world around us. Remember that this is educational and contemplative content that respects all beliefs and perspectives. The scientific information presented is based on publicly available observational data from recognized institutions, such as the Jet Propulsion Laboratory, the Minor Planet Center, and international networks of professional and dedicated astronomers. However, science is a dynamic process, and data on newly discovered objects is subject to continuous refinement as new observations are obtained. Speculations clearly identified as such throughout this narration do not represent scientific consensus, and were included only to illustrate the scientific thought process that distinguishes between grounded hypotheses and established knowledge. Symbolic or archetypal interpretations mentioned briefly are cultural and philosophical, not scientific. If this content helped you relax, learn something, or simply feel a connection with the universe, then it fulfilled its purpose. May you have a peaceful night. May your thoughts find clarity, and may the cosmos in all its vastness accompany you in your rest.